Hello and welcome. Thank you for joining us for today's webcast, How Motorola Solutions Improves Product Development Time, Cost, and Quality with 3D Scanning, sponsored by Capture3D, Rapidform, and TechBriefs Media Group. I'm Billy Hurley, Associate Editor with TechBriefs Media Group, and I'll be your moderator today. Our webcast will last approximately 60 minutes, and there will be a question and answer period at the end of the presentation. If you have a question, you may submit it at any time during the presentation by entering it in the box at the bottom of your screen. Our presenter will answer as many questions as possible at the conclusion of the presentation. Those questions not addressed during the live event will be answered after the webcast. During the webinar, you will also be presented with poll questions, and we invite you to answer those. In order to view the presentation properly, please disable any pop-up blockers you may have on your browser. At this time, I'd like to introduce our speaker. Marian Petrescu is a DSS Greenbelt Senior Mechanical Engineer for Motorola Solutions in Plantation, Florida. With a master's degree in mechanical engineering and over 30 years of experience in design, test, and manufacturing, Marian plays a key role in evaluating, designing, and implementing technology to assist Motorola's product development and quality goals. Marian's research contributed to the development of Motorola Solutions' Rapid Prototyping Center's 3D Metrology Division for reverse engineering and inspection of tooling, parts, and assemblies. He has spoken around the world, sharing his experience and knowledge with the engineering community. So at this time, I'd like to hand the program over to our speaker, Marian Petrescu.
Thank you, Billy. My name is Marian Petrescu. As Billy presented myself, I'm working for Motorola in Plantation. And today, my presentation is about how Motorola Solutions improves product development time, cost and quality with 3D scanning methodology that we implemented here a couple of years ago. As outlined, I'm going to talk about shortly about who is Motorola Solutions, who is Capture3D, who is Rapidform. Then our product development needs at Motorola, use for selecting good metrology system. We're going to mention motion control automation system from Capture3D. We're going to talk about our software tool set for our metrology system, and we're going to talk in detail about Motorola's application using Rapidform XOR and Rapidform XOV as softwares for redesign, reverse engineering, and analysis and verification. Finally, we're going to talk about impact on Motorola's products, introducing our metrology system, a couple of words about future efforts, and finally, we're going to summarize everything. Who is Motorola Solutions? Motorola as a company was founded in Chicago, Illinois in 1928 as Galvin Manufacturing Corporation. The first products for Motorola produced was battery eliminator, which actually was an AC power adapter, car radios called at the time Motorola's or Victrola, and in time Motorola produces police and military radios, transborder for space programs, microchips, pagers, cellular phones, television, satellites, so on. Since January 2011, Motorola separated in two distinctive companies, Motorola Solutions and Motorola Mobility. Motorola Solutions, the company which I work for, is a communication company producing truncated radio system and software for local, state, federal governments, for police and fire departments, produces price scanners, we call them Symbol from the former company producing them, mobile computers, postal terminals, RFID systems. Our facility was founded in 1973 in South Florida Plantation. Here we develop radio, smartphone, and software. There are some laboratories for product simulation, for testing and qualification. And also we have an extensive on-site prototyping operation. We call it Motorola Rapid Prototyping Services, which serves Motorola and other customer development needs worldwide. This is very important. So we're offering services not only for Motorola, but and 4 other companies worldwide. So services provided are CNC machining, tooling, modeling, molding, freeform printing, PC boards, scanning, inspection and verification, and reverse engineering. By curiosity, based on all the products made in Motorola purchases thousands of production tools annually. Internally, we produce more than 600 molds a year. All the aspects, including tool engineering, design, mold flow simulation, tool manufacturing, molding, are in-house. We produce mold with all level of complexity, and we have a rapid cycle time for a mold project, an average one, about 10 days. For more details, you can go to oneprototype.com, our site with our activity since 2008. Who is Capture3D? Capture3D is a company founded in 1998. The company is headquartered in California and has other offices in Washington, Texas, Michigan, and Connecticut. Capture3D is a North American integrator of GOM Germany 3D optical measurement solution, which produce ATOS 3D scanner and trade-off digital photogrammetry. Capture3D has over 4,800 system installation worldwide. Is a company with in-depth process knowledge and experience in various industries like automotive, aerospace, consumer, power generation, casting and forging, injection molding, etc. Is also a developer and manufacturer of standardized and custom automated motion control and robotic solutions. By the way, we have an automated motion control system introduced here by Capture3D. Capture3D is also specializing in implementation of high-quality measurement system and software solution to aid quality control inspection, rapid prototyping, reverse engineering, CFD, FEA analysis, additive or rapid manufacturing. Couple of things about ATOS 3D scanner, which we have it here in plantation. Can capture rapid the geometry, accurate high-resolution data, reliable with stable system architecture, measure small to extra-large objects, various configuration, semi-automation, complete automation, portable, laptop, robotic, etc. Also, Capture3D has an intelligent operating and processing software developed by the same company. Who is Rapidform? Rapidform is a software for reverse engineering and inspection. It's headquartered in Korea with offices in Denver, San Francisco, Frankfurt, and Tokyo. Rapidform is a global leader in 3D scanning software. There are more than 10,000 seats in use worldwide since the company was established in 1998. Rapidform is used at Motorola, at 9 of the top 10 automakers, at 7 of the top electronic manufacturers, at 9 of the top 10 aerospace companies. He is the inventor of parametric reverse engineering software and also the inventor of parametric inspection software. Couple of things about Rapidform XOR software, the software for reverse engineering. Create parametric cage solid models from scans. The fastest path to CAD. Creates native files for ProEngineer, SolidWorks, and other design systems as CATIA, AutoCAD, Unigraphics. Rapidform XOV, the software for analysis and verification, is the fastest geometric dimension and tolerances inspection software. Compare scanned parts to CAD models, automatic parametric repeat inspection. We call this parametric inspection. When path inspection for a part is used for multiple parts. Now we're going to talk a little bit about implementation of 3D scanning metrology system at Motorola. So we started with our product development needs at Motorola where we need different tools, like tools for design, tools for prototyping and modeling, experimentation and testing, and tool for analysis and verification. We focus more on tool for analysis and verification. Here was the kind of activity that we pay attention to introduce a 3D scanning metrology system. So we have to consider, the best choice in implementing the best 3D scanning metrology system. We have certain application in dimensional analysis and verification. Our application are part inspection, part and assembly interaction, part qualification, before and after process or test comparison, tooling cavity number and supplier comparisons, root cause analysis, legacy, ID models, and third-party product support. We also, for dimensional analysis and verification, have certain components. Injection molded plastic parts, insert and over-molded plastic parts, die-cast parts, machine and form metal parts, compression molded parts, PC boards, sub-assembly like switches, speakers, connectors. Another factor to be taken in consideration in choosing the scanning metrology system is the system requirements for our projects here in Motorola Plantation. So in order, the most important for us is speed for setup, scan and post-process, accuracy and repeatability, easy of use for physical process and software, and automation capability, which requires an inspection volume of 300 millimeters cube or weight of 5.5 kilos, 12 pounds. If we have some questions at this point.
Thanks, Marian. At this time, we'd like to present you with our first poll question. The question is, typically, how long does it take for you to receive measurement data for your part in order to inspect or reverse engineer? The choices are A, 1 day, B, 2 to 3 days, C, 4 to 7 days, D, greater than 7 days, or E, uncertain. So in a moment, these choices should appear on your screen, and we invite you to select one of the options. Again, typically, how long does it take for you to receive measurement data for your part in order to inspect or reverse engineer? 1 day, 2 to 3 days, 4 to 7 days, greater than 7 days, or you're uncertain. Back to you, Marian.
Okay, so I don't see the answer here on my screen. I mean, supposed to be a table for the answer here.
Marian, those answers will come in later, and then we can look at those results if we want, or share them at the beginning of the Q&A.
Okay. So is this the only question so far?
Right, so you can continue the presentation. We'll present another poll question later.
Okay. Going forward with selecting the metrology system at Motorola, the type of the system is very important. So we took in consideration contact types or non-contact types of destructive types. So after a survey and considering all the advantages and the issues with the system, we decided to go with the non-contact type of metrology system. After a deep analysis using DSS Digital Six Sigma methodology, a project called Define, Measure, Analyze, Improve and Control DMIC project, we choose from non-contact types the structure white light system. Of course, this was based on what we talked before about our application, our components, the system requirements, the system types, and also the return on investment. This was a very important factor. So our metrology system looks like in this picture. You see the enclosure of automation. We have a 6 automation system from Capture3D with the camera system in. So then we have the PC units here with hard drive, with software interfaces for inspection, for to capturing data, and for the automation system. So our system is, as I said, consists in a computer unit and the Atos 3D scanner from GOM, Capture3D, an operating software from GOM, V7 Professional, and installed by Capture3D, an automation system by Capture3D, motion control automation system, system integration software, Capture3D, and we are using also some tooling and fixturing made at Motorola. So the automation system has 6 axes, 3 rotary axes, 3 linear axes, and also the scanner head assembly is attached to this automation. What characterizes the automation, Capture3D automation? We can program an automation template or a program or a protocol for multiple scanning sequences. The automation can achieve any physical orientation, retain positioning accuracy within 10 microns, which ensure the repeatability and reliability of the system. Template can be rerun by automation on multiple parts. Also, the system stores templates for different inspection volumes or part orientation. This how V7 Inspect Professional looks like. In scanning mold clip for dimensional analysis, you can see both of the cameras, left and right, capturing the data. You can see here on the left how many scans are merged and a line forming a developed 3D part geometry, and also you can see the scanning process on the picture on the bottom. For larger parts exceeding 300 millimeters cube in volume, we can scan them with the automation provided by Capture3D, but we need to limit the number of automation axes in order to avoid any damages of the automation. We can scan weights up to 15 kilos or 30 pounds with full automation, which is very good. In addition of this automation for reliability and repeatability of the system, we use very simple and low-cost holding fixtures as frames or clamps or custom mandrels for special parts like flexible parts. In this picture we can see a keypad, flexible keypad, rubber material. So we pretty much are covering all the volume for the automation system in fixturing and tooling for scanning. As a software tool set for our metrology system, we use design software, Pro-E, IDEA, SolidWorks. For manufacturing, we're using Mastercam and Cimatron. For dimensional verification, we use a scanning software, Capture3D GOM Atos, an inspection software, Capture3D GOM Atos V7 Professional, automation system integration from Capture3D. Also, we are using reverse engineering from Rapidform, actually Rapidform XOR reverse engineering software from Rapidform. Analysis, for analysis we are using Rapidform XOV, and for documentation we are using also Rapidform XOV. We have some other software for statistical analysis like Minitab and finite element simulation, Abacus or MolFlow. At Motorola we have certain applications should be taken in consideration for our activities. So we have CNC verification, feature verification, mold verification. There are example here in all the pictures, warp pitch verification, shrinkage verification. Today we focus on reverse engineering application using Rapidform XOR and analysis using Rapidform XOV. What we use for reverse engineering in our application, most of the applications are about retooling of legacy parts with missing or uncertain design data. Our case study today is about capturing legacy design data for creating new or modified version of products or accessories. Capturing design intent from physical ID, understanding competitive products models is another application. Creating accurate data for third-party products and accessories to ensure compatibility. For analysis and verification, we can use all parts, tools, and accessories requiring analysis and verification. Of course, within the limits of our automation and our scanning system. Before talking about a case study applying Rapidform XOR for reverse engineering, we're going to show the Rapidform XOR workflow here. So the first step is to import the mesh from Atos 3D scanner into Rapidform software. The second step is to align mesh into the coordinate system of Rapidform software. Then is auto feature segmentation, when the software gives us a clue about all the geometries of the scan part of the mesh data. The next step is to create the model, CAD model in Rapidform XOR. Then check the accuracy of that model with the CAD data to see how close they are, and basically to check the accuracy. The last step is live transfer into a CAD software, even Pro-E or Unigraphics or another CAD software. So our application case study today refers to a legacy part. So it's a part which don't have a good design. The customer had some issues with a feature built for this chassis legacy part for assembling some components and boards on the chassis. So the screw template, the customer is reporting that if he matches up the screw location according to the print, the holes on the fixture template will end up misaligning against the chassis heatsink. So the customer is asking to help correct the print of the fixture. So we decided to correct the fixture, capturing the pattern of the holes on the chassis, and having that pattern we also can fix the drawing. So we concluded that the screw fixture and the print do not match the holes pattern on chassis. The chassis was modified in the past for heatsink attachment. The holes pattern needs to be captured from the chassis heatsink assembly and the screw fixture redesign. For this, scanning to capture the holes pattern and reverse engineering are required. Also, we got the message that the customer tries to use traditional methodologies to solve this problem, and they failed. So probably they failed just because the geometrical feature on the bottom to be captured, the bottom of the holes, because the holes are so small and they're also tapped holes, it's very, very hard to capture them. So we decided to fabricate some standoffs to better visualize all the holes from the chassis. So this was a good step and good idea, because going forward with these standoffs we can easily scan the assembly chassis. So after stand insertion we made a scanning preparation. We scanned the part with ATOS automation system. We obtained the mesh data, an STL file, and next we imported that scan data into Rapidform XOR. We aligned the data into coordinate measurement system of the Rapidform software. We started to model template for the fixture using different mesh sketches into Rapidform software. This is one of the mesh sketch for certain type of holes, tapped holes. This is another mesh sketch for corner alignment holes, and then we cut the corner alignment holes into the template already created. Another mesh sketch for another type for M3 holes, and the cut into the 3D model into Rapidform. Finally, we got all the pattern of the holes into the model. We created the model in Rapidform and live transfer into ProE software. Obtaining that into ProE, we just modified the holes in order to insert all the guides for the screws. And finally, we got the fixture redesigned, refabricated, and you can see the fixture fabricated here, and the physical fixture on the top of the chassis, working in assembling all the boards and components. So the customer was very happy with this job. So for this redesign reverse engineering case study, we spent about 2 days for measuring all features on the part 1 day, for reverse engineering activity another day, comparing with the traditional methodology in measuring all the geometrical feature, and with traditional methodology to reverse engineering to do the redesign. We save about 8 to 10 days in engineering work, so this translating in money is about $12,000 saving for this project, for this particular case. Again, if there are some questions at this point.
Thanks, Marian. At this time, we'd like to present our audience with another poll question. So here is the poll question. If you reverse engineer parts, how long does it take on average? And your choices here are A, 1 day or less per part, B, 2 to 5 days, C, 6+ days, or D, we don't reverse engineer parts. So in a moment, again, those choices should appear on your screen, and we invite you to select one of the options. Again, if you reverse engineer parts, how long does it take on average? A, 1 day or less per part, B, 2 to 5 days, C, 6+ days, or D, we don't reverse engineer parts. So back to you, Marian. You can continue your presentation.
Okay, thank you very much, Willie. So the next in the presentation is another case study of analysis and verification using Rapidform XOV. Prior to this, we're going to inform you about Rapidform XOV workflow. which consists in the importing ATOS 3D scan data and CAD model into Rapidform XOV, align 3D scan to CAD model. The next step is to make a deviation color map for hull deviation or thickness deviation, whatever is required on that study. We can create two-dimensional section measurements according with requirements from the prints or critical dimension that we need to analyze and verify. We can also create different three-dimensional geometric dimension and tolerances as per print, depends of the requirements and how many critical dimensions we have. And finally, we can create an inspection report, which can be a simple inspection report or in more detailed inspection report as a trend analysis. So our case study, analysis and verification application. One of Motorola internal customer requested the tooling and fabrication of several hundred mold linear clip plastic parts. The order was very important for our RPTC mold team, the clip being a part of a retail assembly product to be released on the market. To ensure the consistency of the molding process, the dimensional accuracy and quality of the part, after a design of experiment study, our management decided to perform a dimensional and statistical analysis and verification for 16 parts to qualify the parts for fabrication. So we start the process with the first step, scanning and creating the mesh data for all the 16 parts. Then we import the CAD model into XOV software and the scan data. Alignment of 3D scan data to CAD model. Deviation color map, hull deviation in this case for, you can see the top or the bottom. We can do also thickness or all deviation. We created a 2D section measurement. There were some critical dimensions into a certain section on the part, and we compared each dimension from mesh data with dimension from the CAD design. Also, we created 3D geometric dimension and tolerances on different views. And finally, we created an inspection report, fair document first article inspection report for each one of all 16 parts. So the reports contain a page with information about the project, the customers, then database, then the scan data, and then images with two-dimensional sections with all critical dimensions, all the views with 3D geometrical dimension and tolerances, the values for all the dimensions, the hull deviations pages, and this is a complete rapid first article inspection document. For a deeper analysis and verification based on all 16 rapid first article inspection documents saved, we can create a trend analysis report with deep analysis and statistics for each dimension. So this is very, very deep verification with all the dimensions in tables with statistics like upper limit, lower limit, CK, CPK values, and all the spectrum of the deviation for each dimension. So finally we got the trend analysis report with a page informing about the project, customers, the parts, details with then pages with all the statistics for each dimension, for each 2D section and 3D geometric dimensions and tolerances. So after this analysis, we are confident that our process goes well, and we can process the request from our customers, and we release the part and tooling for fabrication. The benefits using 3D, in this case, 3D automated scanning and inspection. For this, we use a Motorola formula. You can find a lot of ways to calculate the productivity, but in our view, the most important thing to put as a factor into the formula is to has a factor like increasing available data, referring to the key dimension, surface thickness variation. Also another factor, important factor for us, is the improvement in data accuracy using 3D mesh data. Reduction in engineering effort to measure, analyze is another important factor, and also reduction in measurement cycle time. We consider these values here, which are very conservative in this case. So from the formula we got the productivity increases 7 times, which translated in money is about $34,000 saving in engineering work. So the impact on Motorola's products by introducing our metrology system, 3D scanning metrology system, is very important. After an investment of $250,000 and additional software investment, considering that we're doing an averaging of 100 projects per year, we reduce problem-solving effort for a lot of development parts, assemblies, and supply chain issues. Also, we reduce part qualification times. Now we have in-house a solution for retooling of legacy parts, and also we got reverse of investment positive after less than 18 months. So for future, we might have something to improve in our activity, to broader implement rapid fair in our inspection activity, to have in more deep statistical analysis of scan data software, to integrate more with simulation tools, Abacus, Autodesk, Morpro, to extend the surface texture measurement and the CT technology solution, which emphasizes on data, export 3D part data based on effective segregation by density. And also to mention here, we might need to implement the latest in technology from Capture3D triple scan with blue light technology. To summarize all of this, we can conclude that the Capture3D solution, GOM scanner and automation, has met our measurement needs. Addition of Rapidform software has expanded the application and capacity of analysis. We achieve speed, accuracy, and ease of use for the systems and for the software. We achieve reverse of investment goal in less than 18 months. We can support now many product development projects, and we can help to resolve many production and supply chain issues. I would like to thank to Steve Spanudis from Motorola Solution, Peter Pulido from Motorola Solution in helping me to develop and implement this system at Motorola. Henry Weed, Capture3D, to implement our automation system implantation, and Tom Sharon, Rapidform, for helping me in finishing this presentation. Thank you very much.
Thanks, Marian. At this time, we'd like to begin our Q&A. And on the line now, alongside Marian, we also have Catherine Kim and Henry Weed from Capture3D. and Tom Sharon from Rapidform for any assistance and questions. Hi, everybody. So to our audience, if you have a question, you may submit it by entering it in the box at the bottom of your screen. Our first question here is related to Capture3D, so it's probably for Catherine and Henry here. How accurate is the ATOS system, and how much does it cost?
I can answer to these questions, if you don't mind.
Sure.
For example, we have two camera system in plantation here. Camera system for 150 millimeters in volume, cube in volume. Accuracy for this system is within 10-15 microns, which is less than 1,000 of an inch. And also we have a larger camera system, 300 millimeters in volume, cube volume. For larger parts, the accuracy for this camera system is within 40 microns, which means less than 2,000 of an inch. And about the cost of the system, as per my knowledge, is I know they have systems starting with $70,000 for the scanner, computer software, training and maintenance. Our system is more expensive than that. It's more complex.
Here's another question, Marian. Why do you need to use software like Rapidform? Can't you go directly from the scanner to CAD?
There is no way to use the mesh data created by the 3D scanner for a process like machining or molding, or the only field you can use the mesh data is for 3D printing. The rest of the processes requires a parametric data. So Rapidform is, as I know, is the fastest and the best software to change the mesh data into a parametric data, actually based on the measurement on the mesh data.
Here's another question. Do you ever make changes to CAD models to match the real part, or do you always create totally new CAD models?
I always create new parts from a mesh data, from an STL data. But as I know, there is a function in Rapidform to correct the CAD data according with the mesh scan data. The function is CAD correct. So somebody from Rapidform can help me with this question with more details about that.
Yeah, that's correct, Marian. So you can either completely create a new CAD model from a part that you've scanned, or there is the ability to import a CAD model that you've already designed, and the Rapidform software will update that model. It'll essentially tweak the geometry of that model to match the actual scanned part, which is useful when you're trying to just update existing CAD to make sure that it actually matches what you're really manufacturing.
Okay, thank you.
Here's another question. Is there surface preparation for scanning?
Can I answer this question?
Sure, Marian.
Yeah, it's a surface preparation for the scanning. Our system ATOS 4 requires earlier preparation for the scanning process. We're using tempera paint mixed with water and a little alcohol, and also we are using targeting dots to make sure the system aligns different scanning position into a merged 3D mesh data. The last system from GOM, for example, triple scan with blue light technology, improved this a lot. It's even faster and better, and eliminated I think 80% the requirements for this preparation. Am I correct? Rapidform? Not Rapidform, Capture3D?
Hey, Marian. Yeah, this is Catherine from Capture3D. I'm the marketing coordinator here. We actually have, like you mentioned, the ATOS triple scan with blue light technology, and it has definitely improved measurement on shiny surfaces. However, if it's completely reflective or translucent, we will still need to treat the surface. However, we suggest that you let us test your part first and see what we can pick up as far as data goes. Thank you.
Here's another question from our audience. Can the technology be used to scan existing situations on a job site?
Who is going to answer this question? Hello?
I can. This is Tom from Rapidform.
Okay.
So the answer is yes, and I think that question could be meant in a few different ways. But for instance, if I'm guessing what the asker is actually looking for, the scanner is able to be taken to a specific location, and you can scan an object. For instance, if that object can't be moved, you can bring the scanner to it. And there are a lot of folks using the technology to do exactly that, to actually scan things in situ as they are, as they've been manufactured and installed, and then deriving the geometry from that and using that for a variety of different purposes, whether that's reverse engineering or inspection.
Here's another question. How precise are the measurements? Is it possible to get plus or minus 0.005 of a millimeter on a CMM machine part made of 6061 alloy?
Can I answer this question?
Sure, Marian.
Most of the time we're using 150 millimeters camera systems, which scan part within that cube, volume. So the accuracy in this case is within 10 microns, which is less than half of a thousandth of inch, and of course there are many factors to give you a good quality mesh data used for inspection purposes. So you need to pay attention to a very well preparation and for the fixturing used for automation and to make a very good quality mesh in order to capture exactly the accuracy required.
There was a second part to this question as well. Do you still use go, no-go gauges for quality control?
For quality control, yes. In some cases, yes. There are parts with deep cavities or deep holes. You cannot easily have access with the scanning system, so you still use those traditional methodologies.
Here's another question from an attendee. Do you get a clean mesh from ATOS, or does it require work in Rapidform for auto-featuring?
For example, GOM software has the ability to fix the mesh in a pretty intelligent way. Also, Rapidform has an unbelievable function to do that. So both of the software, GOM and Rapidform, can fix the mesh before doing the inspection.
How do you find the center of the hole when converting to CAD?
In Rapidform software, there is a function called mesh sketch. When you create a section to that, let's say, cylindrical or cavity, the hole, you're going to get, as the function says, a mesh sketch, which follows pretty close the geometry required, in this case a cycle. So getting the cycle, you exactly get the center of the cycle, which is the center of the cylinder, of the hole that you need to find the position of.
Here's another question. Does the ProE model from Rapidform have features?
Yes, the ProE model the ProE model obtained from translating the Rapidform XOR model keeps the history tree of all the geometries created. So if you have a protrusion of or a surface or a hole or something else, some other geometry into Rapidform XOR, exporting this in ProE, live transfer this in ProE, you're going to keep this, all these steps, all the tree history of the creation of the part. So you can change them, you can modify them in ProE based on the sketches and the geometries created in Rapidform XOR.
This next question looks like it's directed for Henry Weed from Capture3D. Can this equipment be used on die steel first-offs or approvals?
Yes, this is pretty common for a lot of our customers. They're using it not only to inspect the panels that come off the die, but once the die is in a condition where it's making acceptable parts, then they go back and measure the die surface itself because it's changed quite a bit during the working process. So that records the position or the shape of the die that is making correct parts.
This question can be for anyone here, but can you give an example of how the system resolves supplier and legacy part issues?
Can I answer?
Sure.
So I retain the second, legacy parts issues. Which is the first one? So the question refers to two cases.
I'm sorry, Marian. I was looking through the questions. Did you have a question for me?
Can you repeat the question, please?
Sure. It's can you give an example of how the system resolves supplier and legacy part issues?
For legacy parts issues, I jump into the second example. For legacy parts issues, we just can redesign them using Rapidform XOR. And based on the parametric data obtained from Rapidform XOR, live transferring to ProE or another CAD, design CAD system, you can modify the legacy part, retooling or remodeling or rechanging all the features that you want. So you obtain a parametric data used to, whatever process is necessary to create that part. Even if we talk about machining or molding or another process. So for legacy parts, it's you just scan the part, import the mesh data into Rapidform, create a CAD design in Rapidform and live transfer into ProE. And after that, you can change it or keep it the way that it is if you want to process that part for fabrication.
Here's another question that looks like it might be for Henry from Capture3D. How do you address internal features, for example, measuring geometry at the bottom of a deep bore?
The easiest way to handle data at the bottom of a bore is to use a touch probe. So we have an optical probe that can be used with a scanner. It looks similar to the Ruby stylus that you would find in a CMM. So you can just place the probe tip down the hole, record a point or several points at the bottom of the hole, and then use that to construct a plane or inspect whatever your needs are.
Thanks, Tom. Here's another question. How hard is it to merge scans of internal surfaces and external when a part is needed to be cut?
Say it again, please.
The question is, how hard is it to merge scans of internal surfaces and external when a part is needed to be cut?
Usually when you scan a part, depends of the complexity of the part, you use one project scanning, which is capturing all the data, surface data from the part at in one scanning process, or you use double project, scanning the bottom and the top, and then based of common targeting dots, you can align them and polygonize them, obtaining the entire part. So that's the way to scan a part. Running a single project process or double project process.
Here's another question. Once the CAD mode is created, can it be changed?
So if I correctly understood, the question is, say it again, please.
Sure. The question is, once the CAD model is created, can it be changed?
Yes. Having the history tree of all the steps, creating all the geometries, if you transfer this CAD model created in Rapidform into another CAD software, you have the history tree of the model originally created in Rapidform. So you can define them again. You can change them, of course.
Here's a question for Tom Sharon from Rapidform. Does Rapidform work better with certain CAD packages than others? For example, does Pro-E work better with it than, say, SolidWorks?
Right. So that's actually related to the question that Marian just answered as well. So the Rapidform software, when you're reverse engineering, it can take models out to a few different CAD packages as native geometry, where the whole feature tree comes over from Rapidform and goes into the CAD system. And those are ProEngineer, SolidWorks, and Siemens NX. And then we have also native support for CATIA and AutoCAD, although the feature trees don't come in there. And then, of course, any other CAD or CAM software is supported via Parasolid or IGES or STEP formats, as is typical. And so among the CAD systems where we have what we call live transfer, where it actually takes the whole feature tree out of Rapidform and goes into the CAD system, there are differences between all three CAD systems, and it really depends on how you model the part inside of Rapidform. So the main thing is you have to model the part in Rapidform just like you would model it in that CAD system. So, for instance, a Pro-E operator is going to approach a given part a different way than a SolidWorks operator is. You're going to do features in different orders. You're going to use Boolean operations in different ways, things like that. And that's all dependent on just each CAD system's individual style of making the model. And so in Rapidform, it supports doing it in multiple different ways. The main thing there is that you've got to model it such that it's actually going to rebuild correctly in the CAD system, because the CAD system actually does that. It's rebuilding the model as it's coming in from Rapidform, feature by feature. So if it can't solve a given geometry, it will fail, and you'll need to pause the transfer process and address that issue before continuing on with transferring the rest of the features over.
Thanks, Tom. We have time for one more question, and this question is for Henry Weed from Capture3D. Can assembled parts be scanned?
Sure, as long as we understand that the scanner is not an X-ray machine, so there are some obstruction issues. Generally, we will measure the part the best we can when it's assembled, and then using a couple different techniques, either with targets or best fitting, remove parts of the assembly and then scan them individually. And when you remove a part from the assembly, then you have more access to other structures, and you just keep taking things apart until the whole assembly is measured.
Thanks, everybody. That'll conclude today's webcast.